Just like Chapter 9, we have some problems associated with proportions that we just covered, and then some dealing with means. Okay, so I'll do means next, and they have a bunch of cases in the book, but the only case that we'll focus on is the most common. It's when we don't know the variances or standard deviations, and we assume those variances and standard deviations are also unequal. That's going to be the most common one, so we'll just focus on that. And then the paired samples portion of the book is optional. Okay. So just like we saw before, our equal sign will be in the null hypothesis, and we're basically just changing the symbol now. Now we're using population mean, so the mu symbol, instead of the proportion. Okay, so equal sign will always be in the null. The alternate hypothesis or the claim will either have the not equal to sign, the less than sign, or the greater than sign. And this can also be written as this. So just like we saw with the proportion problems, you can actually do, mu1 subtract mu2 from mu1 equals the difference of 0, typically 0. I think it's easier to do it this way because, generally the problem is sort of saying, is the before less than the after? Do we expect the before to be greater than the after? So to me, just intuitively, it makes more sense. You can do it either way. The sign will be the same. The result will be the same. Okay, so this is what I'm talking about. Known variances, very unlikely. Unknown variances, assumed equal is also unlikely. So we will just focus on unknown variances, assumed unequal. Okay, so and this is what Megastat is actually doing for us. You can see that 2 sample means are involved, 2 sample standard deviations, and 2 sample sizes. You're basically comparing 2 samples. Okay, so let's say we wanted to compare the GPA of randomly chosen college juniors and seniors. Because we've got a group of juniors and a group of seniors, they're independent. They're not the same group getting 2 different treatments, let's say, like a weight loss program. You're not the same group of people with their weight before and their weight after. You're 2 different groups of people. Our sample for juniors is 15 people, and we came up with a mean of 3.05 GPA with a standard deviation of 0.2. For seniors, it was 3.25 with a standard deviation of 0.3. Also got 15 people from that population of seniors as well. Assumed variances are unknown and unequal. That's the only case that we'll do in this class. Left tail test, alpha of 0.05. So basically what we're saying when we say left tail test is keeping it in this order, juniors should be less than seniors. Maybe they're just saying a lot of seniors have done all the required classes or have more electives, so their GPA might be higher. So juniors less than seniors is the claim in the alternate hypothesis. Is junior less than senior? Okay, so basically if we can reject the null, then we would say yes here. Okay, hypothesis test. Now we're going to go to compare 2 independent groups. So before we were doing proportions, and now we're just doing means. So we're comparing 2 independent groups. Okay, and we saw this in Chapter 9. We either have the option to enter the raw data or the summary input, which is basically a label, a mean, a standard deviation, and a sample size. For this class, we'll only be doing the most common one, which is the unequal variance. Okay, so you can either select the entire data set or use the mean, standard deviation, and sample size as your summary input, as I said. For this class, we're always going to say hypothesized difference of 0, which is the most common, and confidence level of 95%. Okay, you need to enter the summary input in this format. Label first, then the mean, standard deviation, and sample size as a column. Okay, so we'll do it for both groups, the juniors and the seniors. Okay, then make sure summary input is checked, and then group 1 is selected for junior. Group 2 is seniors, so you select that column. Make sure this is 0 and that this is checked, and we're saying that junior should be less than senior, so we have a less than sign. And hit OK. Okay, I get a test statistic of negative 2.148 and a p-value of 0.0210. So since that p-value is less than alpha, our p-value of 0.021 is less than our level of significance, We reject the null and support the claim that juniors' GPA is less than seniors. Okay. 0.02 less than 0.05, reject the null and support the claim that junior GPA is less than senior GPA. Every time I reject the null, I'm supporting the claim. Okay. Remember, the null is always kind of the nothing's changed. You know, the equal sign's always going to be in the null. And what if I'm a junior and I don't like that conclusion? You know, someone proved that junior GPA is less than senior GPA. Can I change the conclusion? Well, yeah, I can change the confidence level. Let me just up the confidence level to 99%, which means my level of significance is now 1%. And 0.012 is not less than 0.01, so I cannot reject the null. That means I go with the null, and there's no evidence for the alternate hypothesis that junior GPA is less than senior GPA. So again, here's a case where the confidence level is going to change the ultimate decision. Okay, so, you know, if you want it a certain way and your boss or whoever you're doing the research for is okay with a certain level of confidence, then go with what tells the right story for you. You know, it's close enough. Okay, so let's look at some other examples.